There's a cooling system buried under ancient Iranian cities that has been running continuously for 4,000 years without a single electric bill. Air is pulled through pipes buried 6 feet underground, where soil temperature stays at 55 degrees year-round, and delivered into homes at a temperature no modern air conditioner can match for cost. Science Direct published the research. Why did modern builders never mention it? Two things explain why a cooling technology documented in peer-reviewed engineering journals, used continuously since 2500 BCE across the hottest cities on Earth, never appears in the conversation builders have with homeowners about how to keep their houses cool. One involves the physics of why buried pipes work, which most people have never been taught, and which takes about 60 seconds to understand once someone bothers to explain it. The other involves who profits from a $3,000 air conditioning unit installed in every new home in America, and who loses when the alternative is a pipe in the ground. By the end of this video, you will understand exactly how Earth air heat exchangers work, why ancient Persian engineers built cities that stayed cool in 110-degree desert heat without electricity, what peer-reviewed research published in Science Direct has found about the temperature reductions this system delivers, and why a technology 4,000 years old that still works today has been almost completely absent from the conversation about how modern homes are built. The place to start is not with Iran, it is with the ground beneath your feet. 6 feet below the surface of the Earth, in almost any location on the planet, the soil temperature is stable. Not approximately stable, genuinely, measurably, consistently stable across seasons, across years, across decades of surface temperature swings. That would make a thermometer at the surface look like a seismograph reading. The frost line drops that far in cold climates, bringing winter cold down with it. The summer heat penetrates down from the surface in hot climates. But at 6 feet and below, these fluctuations average out into a constant. That reflects the mean annual air temperature of the region rather than any particular day or season. In most of the continental United States, that constant sits between 50 and 60 degrees Fahrenheit. In much of Europe, similar. In the deserts of Iran, where temperatures at the surface reach 110 degrees in summer and drop below freezing in winter, the soil 6 feet down maintains something close to the annual mean throughout the year. Deviating by a few degrees at most, regardless of what the surface is doing, geothermal heat pump technology is built entirely on this same principle, and is sold at premium prices to environmentally conscious homeowners as a cutting-edge, energy-efficient innovation. The Earth air heat exchanger is the same principle without the heat pump, the refrigerant circuit, the compressor, or the electricity. It trades mechanical efficiency for mechanical simplicity. You do not get the controlled precision of a heat pump. You get free cooling from a pipe. This is not a new discovery. It is a basic property of soil thermodynamics that has been understood by anyone who has ever dug a deep enough hole in summer and felt the cool air rising from it. Ancient farmers understood it for their root cellars. Ancient grain storage operators understood it for their underground stores. Ancient city builders in Iran, Egypt, and across the Middle East understood it for something considerably more ambitious. Stay with me, because what ancient Persian engineers built using this principle is where the story becomes remarkable. The system is called an Earth air heat exchanger, or by its original Persian and Arabic designations, the Qanat system and its architectural descendant, the Bagir or wind catcher, combined with underground channel networks. The ancient city of Yazd in central Iran designated a UNESCO World Heritage Site specifically for its traditional Persian architecture. Has been continuously inhabited for over 5,000 years in a desert where summer surface temperatures regularly exceed 110 degrees Fahrenheit. The city did not survive this heat because its inhabitants were tougher than modern people. It survived because its builders understood something about soil thermodynamics that the modern construction industry has largely forgotten. Traditional Persian homes in Yazd were built with underground chambers connected to windcatcher towers above the roofline. The windcatcher, called a bagger in Persian, captured prevailing winds at height and directed them downward into the building. Before that air reached the living space, it passed through underground channels or chambers, where it exchanged heat with the stable, cool temperature of the deep soil. What emerged into the room was air that had been cooled by the earth before it entered. Some systems directed air through underground channels that passed near Qanat water channels, the ancient underground aqueduct networks that transported mountain snowmelt to desert cities, providing an additional evaporative cooling effect as the air passed over flowing cool water before entering the building. Researchers at Atmos documented that windcatcher systems in Yazd lower indoor temperatures by up to 10 degrees Celsius compared to outdoor temperature. Studies confirm their effectiveness has been demonstrated not just in historical accounts, but in modern field measurements of surviving traditional buildings. The system that kept these cities habitable for millennia was not magic. It was physics, understood empirically by engineers who had no electricity, no refrigerant, and no alternative but to make the physics work. The basic principle is elegantly simple. Air is drawn into the system at one end, passes through pipes or channels buried at the depth where soil temperature is stable, and exits into the building at the other end. During transit through the buried pipe, the air exchanges heat with the surrounding soil. In summer, when outside air might be 110 degrees and the soil at pipe depth is 55 degrees, the air entering the building has been cooled by more than 50 degrees through nothing more than contact with the stable thermal mass of the Earth. No refrigerant, no compressor, no electricity, no moving parts, beyond the natural pressure differential that drives air movement. Science Direct published a comprehensive review of passive cooling methods that confirmed the system has been in use since approximately 2500 BCE in Egypt and the Middle East, making it one of the oldest documented engineering solutions to the problem of summer heat in human settlements. The same review documented that modern studies of Earth air heat exchanger performance in comparable climates have found the system reduces indoor air temperature by measurable and significant margins, with some studies reporting reductions of up to 10 degrees Celsius compared to outdoor temperature under normal operating conditions. A separate Science Direct study of buried pipe configurations in the Iranian city of Kerman, one of the hottest permanently inhabited desert cities in the world, with summer temperatures that have historically exceeded 50 degrees Celsius at the surface, modeled the thermal performance of the system and found it capable of delivering meaningful cooling to buildings without any energy input beyond the natural pressure differentials that drive airflow through the pipes. These are not ancient claims from texts that modern science has failed to verify or from folk traditions whose mechanism remains unexplained. They are peer-reviewed engineering studies published in indexed scientific journals, conducted by researchers at universities using computational fluid dynamics modeling and field measurement data collected from operating systems. The physics is not disputed. The cooling effect is real and reproducible. The system works in the same way it worked when Persian engineers first designed it, because the temperature of the soil 6 feet underground has not changed and the laws of thermodynamics have not been revised. Here's where conventional construction and the air conditioning industry diverge from everything ancient Persian engineers understood about how to keep people cool. A central air conditioning system for an average American home costs between $3,000 and $7,000 to purchase and install. It requires an outdoor compressor unit, an indoor air handler, a refrigerant circuit connecting them, ductwork distributed through the house, electrical service sufficient to run the compressor, and a thermostat control system. The compressor consumes roughly 3,000 to 5,000 watts of electricity per hour of operation. In a hot climate, running the system for 8 hours a day through a 4-month summer. That works out to several $100s of electricity per month, every summer for the lifetime of the system. The system itself has a design life of 15 to 20 years, after which the compressor fails, or the refrigerant circuit degrades, and the entire installation is replaced at full cost. The Earth air heat exchanger requires a trench, pipe, and labor to install. Material costs for a residential scale system are in the range of hundreds of dollars rather than thousands. The system has no compressor to fail, no refrigerant to leak, no electrical draw to show up on a monthly bill, and no design life beyond the lifespan of the buried pipe, which in durable materials can be measured in decades or longer. The ancient Qanats of Iran, the underground channel networks that combined drinking water supply with passive cooling, are in some cases still functioning after centuries of continuous use. The comparison is not subtle. It is a system that costs money every month against a system that costs money once, an industry built around annual service contracts, refrigerant recharges, filter replacements, and eventual full system replacement, against a pipe in the ground that does not require any of those things. The air conditioning industry did not suppress the Earth air heat exchanger through any deliberate campaign. What happened is what always happens when a manufactured product and a natural system address the same problem. The manufactured product has a supply chain, a marketing budget, a distribution network, building code language written around it, contractor licensing built around its installation, and a financial ecosystem of manufacturers, distributors, installers, and service companies, whose livelihoods depend on its continued dominance. The natural system has none of these things. It has physics and 4,000 years of empirical validation, and neither of those comes with a sales representative. Building codes in most American jurisdictions do not include standard provisions for Earth air heat exchangers and residential construction. Mechanical engineering curricula at most universities do not routinely cover passive geothermal cooling as a primary residential design option alongside conventional HVAC. HVAC contractor training and licensing is built entirely around active refrigerant-based systems. The result is that an architect specifying a new home does not typically offer Earth air heat exchange as an option, not because it does not work, but because the contractors who build homes have not been trained to install it, and the building codes they work within do not include guidance for it. The knowledge gap is not maintained by active suppression. It is maintained by the ordinary institutional inertia of an industry that has no reason to teach what it has no reason to install. and no reason to install what generates no ongoing service revenue. Here is exactly how the system works at the residential scale, and what the research tells us about its performance. The core installation consists of a length of pipe, typically 4 to 6 inches in diameter, buried at a depth between 4 and 8 feet below the surface, running horizontally from an intake point outside the building to an outlet inside. The intake is positioned away from the building in open ground, typically shaded or oriented to minimize exposure to direct solar heating of the incoming air. The pipe runs underground for a minimum distance, sufficient to allow the air temperature to equilibrate toward the soil temperature during transit, with longer pipe lengths, providing greater temperature exchange and more complete cooling. The University of Maryland published research on residential earth air heat exchanger performance that found systems with pipe lengths in the range of 100 to 200 feet delivered inlet air temperatures within a few degrees of the soil temperature at pipe depth, meaning that outside air entering at 95 degrees Fahrenheit was delivered to the building interior at temperatures between 60 and 65 degrees after transit through appropriately sized buried pipe. The temperature reduction was consistent across the cooling season and required no energy input beyond a small fan, which in some traditional designs is replaced entirely by the natural pressure differential between the warm exterior and the cooler interior. A 2021 study published in Energy and Buildings Journal modeled the performance of earth air heat exchangers in hot desert climates, and found that a well-designed system could reduce cooling energy demand in buildings by between 30 and 75% compared to conventional air conditioning alone, with the highest reductions occurring in the climates where cooling demand is greatest and where the temperature differential between surface air and buried soil is therefore largest. The same study noted that the Persian wind catcher Kanat combination systems ancient engineers developed represent an optimal implementation of the same principles that modern earth air heat exchanger engineering has independently validated. The humidity question is one that research has also addressed honestly. In dry desert climates, the earth air heat exchanger delivers cool, dry air with no humidity concerns. In humid climates, the system can deliver air that is cooler than ambient, but potentially carries higher relative humidity than the building interior requires, which is a design consideration rather than a fundamental barrier. Modern implementations address this through condensate drainage points in the pipe runs, allowing moisture that condenses on the cool pipe walls to drain away rather than entering the building. This is standard engineering practice for any system that moves cooled air, and it adds modest complexity to the installation without compromising the fundamental operating principle. The installation process is within the reach of any homeowner with access to a trenching machine, available at any equipment rental company for a few $100s per day, and basic pipe fittings. The pipe itself is standard 4-inch PVC drainage pipe, available at any plumbing supply house. The inlet requires a screen to exclude insects and debris. The outlet requires a simple register or grill. The buried section requires no maintenance, produces no emissions, consumes no energy in passive configurations, and does not degrade in function as long as the pipe remains intact underground, which, for PVC in most soil conditions, means a lifespan measured in decades at minimum. Your air conditioning bill last month represented electricity consumed to move heat that was already inside your house to a location outside it, using a compressor and refrigerant circuit that will eventually fail and cost several $1,000s to replace. The earth 6 feet below your lawn has been sitting at 55 degrees all summer, the same temperature it was last summer and will be next summer and every summer after that, for as long as the climate of your region maintains its mean annual temperature. It has been waiting, with perfect geological patience, for someone to run a pipe down to it and let the physics do what ancient Persian engineers figured out it would do 4,000 years ago. The building industry in the country with the highest air conditioning penetration rate in the world has not mentioned it. The builders who constructed your house did not offer it as an option because the contractors they hired had never been trained to install it, and the building code they followed included no guidance for it. The HVAC company that services your system has no product to sell you that involves burying a pipe in your lawn and connecting it to a vent. The utility company that bills you every month for the electricity to run your compressor has no particular interest in a technology that reduces your electricity use by 30 to 75%. None of these parties suppressed the knowledge of what ancient Persian engineers built. They simply had no reason to transmit it. The ancient city of Yazd still stands in the Iranian desert. The traditional homes with their wind catcher towers still demonstrate the principle. The UNESCO designation that protects it acknowledges the sophistication of what was built there. The research papers confirming the physics are published in Science Direct. The temperature in the soil under your property is stable right now, exactly as it has always been. At a depth, a competent contractor with a rented trenching machine could reach in an afternoon. The ground is still 55 degrees. The physics has not changed. The pipe still works exactly as it worked in Yazd 4,000 years ago. The only thing that changed was who was responsible for building your house and what they had been taught to build. If you found this genuinely useful, watch the next video and do not forget to subscribe. See you in the next one.